Close your eyes for a moment and think about the ocean. The Pacific, the deepest point on Earth, the Challenger Deep in the Mariana Trench, descending nearly 11 kilometers into the darkness. 11 kilometers of water above you, pressure increasing with every meter of depth, the temperature dropping, the light fading, until at the very bottom you are in a place so remote and so crushing that fewer humans have visited it than have walked on the moon. 11 kilometers deep. On Earth, that is the deepest ocean we have, the most extreme aquatic environment our planet produces. Now imagine an ocean not 11 kilometers deep, not 100 kilometers deep, not 1,000, an ocean hundreds of kilometers deep, an ocean so deep that the entire height of Earth's atmosphere, from the surface to the edge of space, could be submerged within it many times over, an ocean in which our entire planet could be swallowed without touching the bottom. This ocean exists. Not on Earth, not in our solar system, on a world orbiting another star entirely, a world so dominated by water in all its exotic, high-pressure, extreme temperature forms that it belongs to a category of planet we have only recently been able to identify and study, a water world. And the water worlds we have begun to find are not merely planets with more ocean than Earth. They are planets that are almost entirely ocean, worlds where water is not a surface feature, but a fundamental component of the planetary structure itself. Worlds where the concept of a seafloor, the solid boundary that defines where ocean ends and rock begins, exists hundreds of kilometers below the surface, under pressures so extreme that the water above it is no longer liquid in any sense we would recognize. This is a story of the most extraordinary water worlds ever discovered, and the science of what lies inside them is stranger, more beautiful, and more terrifying than any ocean on Earth has ever been. Earth is sometimes called the blue planet, and from space, the description is apt. 71% of Earth's surface is covered by ocean. The Pacific alone is larger than all of Earth's land masses combined. But Earth is not a water world, not by the definition planetary scientists use. For all its oceans, water makes up only about 0.02% of Earth's total mass. The planet is predominantly rock and iron, a thin film of water on the surface of a fundamentally rocky world. A true water world, a planet where water constitutes a significant fraction of the total planetary mass, perhaps 10 to 50% or more, has an interior structure completely unlike Earth's. Imagine starting at the surface of such a world. The upper ocean is liquid water, familiar enough. Temperature and pressure within the range that water remains in its liquid state. Light penetrating from above if the star is close enough and the atmosphere thin enough. A surface ocean perhaps hundreds of kilometers deep already, deeper than anything on Earth. But keep going down. As depth increases, pressure increases enormously, the weight of hundreds of kilometers of water above pressing down on everything below. At sufficient depth, perhaps a few hundred kilometers beneath the surface, the pressure exceeds what water can sustain in its ordinary liquid form. Here, something extraordinary happens. Water transitions into a different phase, not ice in the ordinary sense, not the ice you find in your freezer which forms at low temperature and relatively low pressure, but high-pressure ice, a form of water called ice VI, or at higher pressures, ice 7, that forms not because of cold but because of the crushing weight of the ocean above it. This is hot ice that exists at temperatures that might be hundreds of degrees above zero. Not cold, not frozen in any intuitive sense, but structurally crystalline because the pressure forces water molecules into a lattice regardless of temperature. Below the ice layer, deeper still, pressures become so extreme that even the high-pressure ice phases give way. The water enters states that we have only recently begun to characterize in laboratory settings. Superionic water, a phase where the oxygen atoms form a crystal lattice while the hydrogen ions flow freely through it, like a liquid conductor, a solid and a liquid simultaneously, an electrical conductor. And below all of this, below hundreds of kilometers of liquid water, high-pressure ice, and superionic water, there may be a rocky core, Or perhaps not. In some water worlds so rich in water that rock is a minority component, there may be no conventional rocky mantle at all. Just water in its various exotic phases all the way to the center. A planet made almost entirely of one molecule, H2O, in all its extraordinary forms. And we have found planets that appear to be exactly this. For years, water worlds were theoretical. Planetary scientists built models, calculated what a planet with a large fraction of water by mass would look like, predicted its radius, its density, its internal structure, created a category. But a category without examples is speculation. Then we built the instruments, and the examples came. One of the most compelling candidates is a planet called GJ1214b. GJ1214b was discovered in 2009, orbiting a small red dwarf star approximately 40 light-years from Earth. Its radius is about 2.6 times Earth's radius. Its mass is about 6.5 times Earth's mass. When you calculate the density from those two numbers, mass divided by volume, you get a density much lower than Earth's, much lower than you would expect from a rocky planet, much lower than you would expect from any planet whose interior was predominantly iron and silicate rock. The only way to reconcile GJ1214b's size and mass is to give it a significant fraction of low-density material, water. Planetary models suggest GJ1214b could be composed of approximately 25 to 35% water by mass, compared to Earth's 0.02%, an ocean world on a scale that dwarfs anything in our solar system. James Webb has since studied GJ1214b in remarkable detail. Its atmosphere, whatever it contains, is obscured by a thick layer of high-altitude haze or cloud. Webb's infrared observations have so far been unable to fully penetrate this layer to characterize the atmosphere beneath. But the planet's bulk properties, its size, mass, density, remain consistent with a water-dominated interior. And GJ1214b is not alone. TOI 14252b, discovered in 2022, orbits a red dwarf star about 100 light-years away. Its radius is approximately 1.67 times Earth's, its mass approximately 4.8 times Earth's, and its density is strikingly low, again consistent with a water mass fraction that could exceed 30%. Kepler has found dozens of planets in the size range between Earth and Neptune, called sub-Neptunes or mini-Neptunes, that have bulk densities consistent with significant water content. The population of potentially ocean-dominated worlds in our galaxy may be vast. But perhaps the most intriguing recent discovery is a system that rewrote expectations about how common ocean worlds might be: the TRAPPIST-1 system. 7 Earth-sized planets orbiting an ultra-cool red dwarf star just 39 light-years away. 3 of them in the habitable zone, and density measurements from the gravitational interactions between the planets suggesting that several of them contain substantially more water than Earth. TRAPPIST-1 planets B, C, D, E, F, G, and H, densities measured through a process called transit timing variations, tracking the tiny gravitational tugs that planets exert on each other as they orbit, all come in lower than pure rock would predict. Some models suggest water mass fractions of several percent for the TRAPPIST-1 planets. Several percent sounds modest, but Earth's water fraction is 0.02%. A TRAPPIST-1 planet with even 5% water by mass would have oceans hundreds of kilometers deep. Oceans that are not just surface features, but structural components of the planet itself. A handful of rocky planets within 40 light-years of Earth, potentially hosting oceans deeper than Earth's atmosphere is tall. The water worlds are real. They are close, and they are raising the most profound question in planetary science. Can anything live in them? Life on Earth began in water. The earliest life forms were aquatic, single-celled organisms in warm, chemically rich environments, possibly around hydrothermal vents on the ocean floor, where the heat and chemistry of Earth's interior met the ocean above. Life that needed no sunlight. life driven by chemical energy rather than photosynthesis. These hydrothermal vent ecosystems exist today. In the deepest parts of Earth's oceans, communities of organisms live in complete darkness, fed by the chemical reactions between hot vent water and the surrounding rock. Tube worms, crabs, shrimp with no eyes, bacteria that oxidize hydrogen sulfide for energy. No sunlight, no photosynthesis, life powered entirely by geochemistry. This is relevant to water worlds because in a true water world with hundreds of kilometers of ocean above a high-pressure ice layer, sunlight never reaches the seafloor. Not a little light, no light, ever. But if that world has geothermal activity, if the rocky core is still warm from its formation or from radioactive decay, if heat and chemical energy are available at the boundary between the deep ice and whatever lies below, life might not need the sun. It might thrive in the dark, in the pressure, in the chemical gradients between hot rock and cold deep water. However, there is a complication, a critical complication that makes water worlds more complex as habitats than they might initially appear. Life as we know it depends not just on liquid water, but on chemistry, on the cycling of elements, carbon, nitrogen, phosphorus, sulfur, the elements of biology. These elements need to move from the geological interior to the ocean where life can use them. And in a water world with hundreds of kilometers of high-pressure ice between the rocky interior and the liquid ocean above, that cycling is inhibited. The ice layer acts as a barrier. On Earth, plate tectonics continuously cycles material between the mantle and the seafloor. Volcanoes erupt nutrients. Seafloor spreading creates new crust and exposes fresh rock. The ocean and the rock are in continuous chemical communication. In a water world, that communication may be blocked by the ice. Some models suggest that the high-pressure ice is not a perfectly impermeable barrier, that chemical exchanges can still occur across it, particularly if the ice layer is thin enough or if convection within the ice creates pathways. That geothermal heat from the core can still drive chemical cycling even through the ice. Other models are less optimistic. The answer, whether water worlds can cycle nutrients efficiently enough to support biology, depends on the specific thickness and properties of the ice layer, which in turn depends on the water fraction, the planetary mass, the internal heat, and a dozen other parameters that vary from world to world. Some water worlds might be chemically isolated dead oceans, water without biology. Habitable in the sense of containing liquid water, but not in the deeper sense of containing the right chemistry for life. Others might be the most abundant habitats in the galaxy. If life can survive without sunlight and without the direct cycling of rock and ocean, then any water world with a warm enough interior is a candidate. The universe may contain more ocean than it contains of anything else. And in all those oceans, in all that water, in all its exotic phases, under all that pressure, the question of what lives there is one that will define astrobiology for generations. We have always been drawn to water, not just for survival, not just because our bodies are 60% water and our cells require it, and without it we die in days. Something deeper than survival. Something that sends people to stand at the shore and look out at the horizon and feel something that has no clean name. Something that makes the ocean feel both alien and familiar, both threatening and welcoming, both completely different from us and somehow deeply ours. We came from the ocean. Every multicellular animal that has ever lived on this planet is descended from aquatic ancestors. The salt content of our blood is a memory of the ancient sea. The rhythms of our hearts are descended from the gill pumping of creatures that lived hundreds of millions of years ago in warm, shallow water. We carry the ocean inside us. And now we are finding that the ocean, water in all its remarkable properties, may be among the most common substances in the universe as a planetary material. Not just a surface feature of fortunate worlds, a fundamental planetary building block, a material that under the right conditions dominates entire worlds. Water worlds may be common, possibly very common. The density measurements of exoplanets are still imprecise, still debated, still subject to revision as better data comes in. But the trend in the data suggests that planets with significant water content, far more than Earth, far more than anything in our solar system, are not rare. If that is true, it changes something. It changes what we mean when we ask whether the universe is hospitable to life. We used to imagine life needing something much like Earth, a rocky planet, the right distance from the right kind of star, liquid water on the surface, plate tectonics to cycle nutrients, a magnetic field for protection, a large moon for stability. A very specific recipe. A recipe that, if all the ingredients have to be present simultaneously, might be rare. But if life can start and persist in a dark, pressurized ocean beneath hundreds of kilometers of ice, without sunlight, without plate tectonics as we know them, powered by the slow leak of geochemical energy from a rocky core, then the recipe is simpler. Star, planet, water, heat. Those ingredients are everywhere. Stars exist in the hundreds of billions. Planets appear to be the natural consequence of star formation. Nearly every star likely hosts them. Water is one of the most common molecules in the universe, formed wherever hydrogen and oxygen meet in sufficient quantities. And heat, internal heat from formation, from radioactive decay, from tidal flexing by nearby gravitational influences, is available to planets at enormous distances from their stars. A water world in the habitable zone is not required. A water world anywhere with sufficient internal heat might do. And if that is true, if the ocean worlds we are finding represent habitats rather than dead ends, then the universe is not mostly empty. It is mostly ocean. Hundreds of kilometers deep, dark, pressurized, ancient.